Okay, so yeah, we can chat for a bit and then we can start even a minute or two late, which is
Sure.
fine.
Yeah.
Cool. So are you all settled in York?
Yeah, I've been here more than a year now. Kind of
Ah,
said, yeah.
time flies really.
I know, I know. This week has been really busy because I was on the LOC and SOC for the Canadian version of the AAS. So it's just 400
Mm,
people, just conference anyway.
have fun. I know. It's fun to organize conference, but they suck the soul out of you.
I wouldn't call it fun, but yeah.
So I just organized the Space Telescope Spring Symposium, and
Right.
I know it's a 200 people conference, but seeing 200 people in my backyard, Space Telescope cafeteria, it's quite nice.
Yeah,
That's the fun part, but the rest of it isn't great.
right, right.
Okay, I see that we have a few people joining us in respect of everyone's time. I think we should just start on time, and the recording will be available on YouTube afterwards. So yeah, hopefully more people will catch the recording. So today we are presenting you the last seminar planned for the 2023 to 2024 school year of the Galaxies SIG. And of course, we have an amazing lineup in the fall as well. So come back and check in. We will restart in September. So just look out for an email from us. And if you're viewing this from YouTube, this is the last talk of the season of the year. Okay, so today we have Rahul Kannan joining us from the York University. So I've known Rahul for a while now, and I just was catching up with his career trajectory. So Rahul got his PhD from the Max Planck Institute for Astronomy, MPIA at Heidelberg, and also the University of Heidelberg. And then he was a postdoc at MIT, and then a NASA Einstein Fellow and Harvard ITC Fellow at the CFA. That's when I met Rahul, and then start talking to each other. Okay, so today Rahul is going to tell us about modeling the interstellar medium of galaxies. Rahul, take it away.
Yeah, thank you, Aaron, and thank you, Benny, for inviting me to give this talk. So today I will, as Aaron mentioned, I'm an assistant professor here at York University. Just started about a year ago or so, and today I will talk about modeling the interstellar medium of galaxies, specifically focusing on medium to high resolution simulations that can model the multi-phase structure of the interstellar medium. So we all know, since this is a Galaxies working group, we all know how a galaxy looks like. But just so that we are all on the same page, the galactic ecosystem is a very complex ecosystem. It is made up of a lot of different parts, like galactic gas inflows from the large scale structure, mergers from other galaxies, and then you have other physical processes like radiative heating and cooling. You have star formation, of course. Then you have stellar evolution, which injects metals and dust into the surrounding medium. And then you have feedback from stars and black holes. This is mainly energy and momentum injection from stars and black holes. And finally, you have other complex processes like radiation fields, cosmic rays, turbulence, thermal conduction, etc., etc., etc. I can keep going, but this is just a simple list of other processes which also impact the properties of galaxies. So the ISM, in general, is the high density part of a galaxy. So densities of about greater than 1 or 10 particles per cc is generally considered to be the ISM of a galaxy. It is generally multi-phase. So it ranges from a range of densities and temperatures. So going from about 1 to about 1,000 or even 10,000 particles per cc and even higher in this really dense star-forming regions. And it also varies in temperatures from very cold gas to from about 10 Kelvin to all the way to 10 to the 4, 10 to the 5 Kelvin or so. And it contains bulk of the metals and dust in the galaxy, so it's a very important phase. It also contains giant molecular clouds, which are the sites of star formation. And as I mentioned before, various processes, physical processes like cooling, feedback, radiation, et cetera, can impact how the phase space structure of the ISM looks like. Okay, and so this is just an image of a very nice image from of Galaxy NGC 628 showing the various different components of nearby galactic disk. So how does the HWO, Habitable Worlds Observatory, fit into all of this? So it promises to provide exquisite spectroscopy and high resolution imaging in the UV. So it can help us detect inflows and outflows using absorption and emission line diagnostics from individual star forming regions from nearby galaxies. So it's ideal for figuring out the complex physics that goes on in the ISM of galaxies. And as you can see here, I just took these some example spectra and the angular resolution of the Habitable Worlds Observatory from the talk given by Jason Tomlinson here. And as you can see, you have very good spectroscopy and imaging capabilities. And it is, so since you can get this very nice data from the observations, theoreticians have to go and put more work in order to make full use of the data that will come from these telescopes. And so that's where people like me come in, and where we are trying to model the ISM of the galaxies so that we can try to understand what the observations are telling us. So there are a lot of different models of the interstellar medium. I won't be talking about all of them, but I will class them into three different classes. The first is modeling the ISM using a small patch of the galaxy. So you take a very small patch, about 1 to 2 kiloparsecs on a side, and then you evolve this very small patch of the interstellar medium with extremely high resolution. So some examples of these simulations are the Tigris project from Eve Ostriko's group, Silk simulations from Stephanie Walsh in, I think, in Cologne. What the advantage of these simulations is that because it's a very small patch of the ISM, you can actually put a lot of resolution elements in them. And so you can actually do almost first principle simulations of cooling, heating, feedback, etc. And you can try to understand how these small scale processes impact the large scale properties of the galaxies. And one such model is this pressure regulated feedback modulated model of the ISM from Chang-Gu Kim and Eve Ostriker. I won't go too much into the details. You can look at their paper for more details. Another class of models for modeling the ISM is, of course, medium resolution or medium to high resolution galaxy formation simulations. FIRE is a very good example of these class of models, where they take cosmological initial conditions from a large box and they zoom in on an individual galaxy, and they put a lot of resolution elements into this individual galaxy so that they can resolve, well, at least partially resolve the multi-phase structure of the galaxy, of the ISM in these galaxies. Okay. Of course, since these are cosmological zoom-in simulations, you still are not able to resolve all the processes. For example, supernova feedback is a subgrid model in this kind of galaxy formation model. But you can kind of get the multi-phase structure of the ISM correct. So these simulations have also been very successful in modeling the large-scale properties of galaxies. Finally, the third class of simulations are these very large-scale, hundreds of megaparsec scale simulations, like Illustris TNG, Millennium TNG, Eagle, Owls, etc., etc. Of course, since these are modeling very large representative volumes of the universe, you cannot really resolve the ISM very well. Okay, so you need to have some kind of an effective model to model the ISM of the galaxies, because you do not really have the resolution to model the ISM properly. So what most of these models do is to use something called the equation of state, which is like something called an effective equation of state, which kind of takes care of heating and cooling in the ISM in a subgrid manner. Okay, and by doing that, you get rid of a lot of computational complexity that arises from modeling the ISM, so that you can model a lot of galaxies, but not as well. Okay, so that is this third class of models. Okay, so here in this talk, I will kind of focus on the second class of models, and I'll be talking mainly about my attempt at modeling the ISM properly. So here I'll mainly be talking about my 2020 paper, where I introduced this ISM model called Smuggle RT. What it does is it couples multi-phase ISM to radiation fields with the Arepo RT code. It has better low temperature cooling because it follows the non-equilibrium abundances of molecular hydrogen. And this molecular hydrogen, and I must say that we also follow the evolution of dust grains. And so you know for each patch of the ISM how much dust is present, and because we know how much dust is present, we can also model the formation of molecular hydrogen on dust grains. So you have this coupling between dust, molecular hydrogen, and radiation all together. And since it is fully coupled radiation hydrodynamic simulation, it can also partially or fully model the H2 regions around newly formed stars, the H2 ionized H2 regions, and even the photodissociation regions. And similar to fire and other models, it also follows, we cannot really resolve the supernova feedback. So we use this boosted momentum injection that was first discussed by Kim and Oestreicher in 2016. Okay. So the reason for modeling this is because the reason for going to these kinds of models is that you get a much better ISM. So here I show the phase space structure of the central galaxy in a simulation. On the left is a cosmological simulation called Thiessen that I did about 2 years ago or so. And that's the phase space structure. And on the right is the phase space structure of the gas in the galaxy with this new ISM model. And so on the left, you can see here, if you can see my mouse, that here on this high density regime beyond 0.1 particles per cc or so, all the gas is in this effective equation of state. That's the subgrid models that most of these Illustris and TNG and Millennium TNG simulations use. So they cannot really, there is no multi-phase ISM present. It's all the gases in this equation of state. But now with this new additional cooling and radiation fields and dust and everything put together, you can actually model the multi-phase structure of the gas. So you have the ISM is not just composed of an equation of state, it is now composed of different states of the gas, cold dense gas, hot, ionized gas, everything together, mostly in pressure equilibrium. And you can also see this structure here, which is a lot of gas in this 10 to the 4 Kelvin, high density gas, which are these H2 photoionized regions, which are kind of resolved in this ISM model. So as an example of the capability of this model, I want to show a mock image from the simulation of a Milky Way-like galaxy. I must stress that this is not post-processed in any way. I'm just showing what automatically comes out of the simulation. So the red is automatic. The red here in the RYB image is the IR band of the radiative transfer. So the radiation field, the IR radiation field is self-consistently followed. So you just take the IR radiation field, and that is denoted as red. Then you take the optical radiation field, which is denoted as yellow, and you take the extreme ionizing radiation field, which is denoted as blue, and then you make a mock RYB image. And I just want you to concentrate on one single star forming region here. So this region here, as you can see my mouse, it is currently obscured. It is currently red because it's mainly IR, because most of the radiation coming from new stars is being reprocessed by dust and being re-radiated in the IR. So that's why you see this as IR bright. Now I'll run this movie along, and you can focus on that region, and you can see that this radiation field is clearing out a path, and you can see the ionizing radiation coming out. And finally, you have supernova explosions, which create super bubbles around this region. And you can see these dusty shells, low density gas and dusty shells around this expanding H2 region and the supernova bubble. So you can actually model all the important processes that is going on in the ISM of galaxies, okay? So that was just a qualitative image. So more quantitatively, here I show the distribution of molecular hydrogen, both face on and edge on in this Milky Way-like simulation on the left. And on the right is the molecular Kenniget-Schmidt relation. And you can see for lower molecular hydrogen densities here, we kind of match what the observations tell us, but the central region is deficient of H2, but still seems to be forming stars. So the central region in the galaxy seems to have much lower gas depletion times somehow. And we don't know why that is. That is something we have to look at. Maybe our molecular hydrogen chemistry module is doing something weird there. But yeah, we seem to be kind of in a starbursty phase where the gas depletion times are much smaller in the central galactic zone. Of course, as I said, we also can predict the distribution of dust in these galaxies. So that's what I show here. In green is the dust to gas ratio in the disk of the galaxy. And in the red is the dust temperatures. So bright is about 40 Kelvin dust, bright red or bright yellow, and going all the way from 40 Kelvin to about 5 Kelvin dust, okay? So that's the qualitative image again. So quantitatively on the right top panel, here I show the distribution function of the dust temperatures. And you can see it ranges from about 15 Kelvin to about 50 Kelvin or so. And in the black points are the distribution of dust temperatures in nearby galaxies like LMC, SMC, M31, and M33. And you can see that we kind of match the dust temperature distribution very well. And at the bottom panel is the dust to gas ratios compared to the nearby galaxies again. Again, the distribution is kind of in the same ballpark as the distribution of nearby galaxies, although we seem to have slightly higher dust to gas ratios than what is seen in nearby galaxies. Okay. And so we can also look at dusty outflows. So this was all face-on images. You can also look at edge-on images, and here I'm just showing edge-on images of dusty shells in nearby galaxies from Chris Hauck's 2000 paper. And they are detected in reflection of background starlight or even absorption of background starlight. And these dusty shells and shell-like features in the dust are classic signs of outflows. And you can try to see if we can find those kinds of outflows in our galaxy as well. So I'll play this movie along. And you can see that there are, as the disk evolves, there are these supernova explosions going on, which kind of blow the dust out into not the CGM exactly, but outside the disk of the galaxy. Okay, so you do have these dusty shells and outflows, which you also see from the simulations themselves. So these kind of shell-like, expanding shell-like dusty structures. And so you can try to quantify this more. So this is quantifying how much amount of dust is present in the CGM of galaxies as a function of their stellar mass compared to observations of recent nearby galaxies. So the black points are the observations, and the blue and the red are the simulations. And you can see that we kind of eject the right amount of dust from these galaxies as well to the CGM of these galaxies. So we can also predict how much outflows are there from these galaxies. Okay. So as I said, this is the ISM model kind of predicts the right densities of the gas, the right temperatures of the gas, the right dust distribution in the gas, and it can, because we have full radiation hydrodynamics, we can also predict the ionization structure of the gas. If you have all these properties, it is very simple to then get, well, not simple. Well, we have all the ingredients to get the emission lines from these galaxies, okay? Because you have the ionization state, the dust, and the gas densities, and the temperatures. And these are the most important components necessary to get the emission lines, okay? So here is an example of all the properties, and we kind of post-process this simulation using the radiative transfer code written by Aaron Smith, and then we kind of get emission lines. And so that's what is shown here. So for example, here is face-on and edge-on image of the H-alpha emission that we expect to observe from this kind of a galaxy, okay? And we can not only get H-alpha, just the hydrogen lines. Now we have kind of improved our, we have improved cold, basically. And you can basically not only get just the hydrogen lines, but you can also get oxygen, sulfur, magnesium, neon, all the other important lines, which are important traces of galaxy formation physics, okay? So we can get all these lines properly from these simulations. So again, this is a qualitative picture. So more quantitatively, we can look at, for example, the radial emission profiles of H-alpha in orange, H-beta in blue, and O3 in green. The lines and shaded regions are simulations of a Milky Way-like galaxy, and the points are observations from nearby Milky Way-like analogs. And you see that we kind of reproduce the radial profiles of these emission lines. Not only that, we can also match the kind of emission line ratios. So again, the red line and the shaded region is the Milky Way-like simulation. The blue points are taken from the Fangs-Muse survey. And you can see that we kind of match the line ratios of S2 over H-alpha, O1 over H-alpha, N2 over H-alpha, and O3 over H-beta emission line ratios, which are mainly emission lines which kind of trace, I think, the diffuse ionized gas galaxies. So because you can kind of predict the emission lines, we can try to figure out what these emission lines are actually telling us about galaxy formation physics. Okay, so here is one example of one such analysis that we did. So on the x-axis here is the star formation history. So about anything above 0, your star formation rate is increasing of the galaxy is increasing with time. Anything below 0, the star formation rate is decreasing. Okay, that's the x-axis. And on the y-axis is the star formation rate that you get using the star formation rate H-alpha calibration relations that observers generally use to get the star formation rate from the H-alpha emission of the galaxies. Okay. So 0 means you're exactly on the observed relation. If you're below that, then you're kind of under predicting the star formation rate. Okay, that's how the y-axis works. Okay, so again, this is dust attenuated relation we are already talking about. So the y-axis already corrects for dust attenuation using the Balmer decrement. Okay, so you would assume that since we took into account the dust attenuation using the Balmer decrement, all the simulation points should lie on this 0 line. But that's not what you see. What you actually see is if you have especially if you have increasing star formation histories, you can actually underpredict the star formation rate. And the reason you underpredict the star formation rate of these galaxies is because dust can not only attenuate the H-alpha emission, dust can also absorb the Lyman continuum photons themselves. Okay, and what we see is that about 28% of the Lyman continuum photons which ionize the galaxy, instead of ionizing the hydrogen, it's just absorbed by the dust. So that ionizing photons is no longer present in order to absorb to get absorbed by the hydrogen lines and give you H-alpha. Okay. So that's why you get this decrease in this star formation rate predictions. But if you account for the fact that some amount of Lyman continuum is absorbed by dust, some amount is absorbed by helium, some amount of it, like 6% of it, escapes the galaxy itself, then you can correct for this. So this shaded, well, light pink lines are without this correction. If you correct for the fact that you have some amount of absorption from dust, from helium, and from escape of these Lyman continuum photons, then you get these dark red points, and you're back on this Lyman star formation rate H alpha relation. Okay, so these are the kind of stuffs you can do using these emission line predictions from these simulations. Okay. We also kind of looked at how, if we can understand the nature of diffuse ionized gas in the ISM of galaxies. So on the left, what we are showing is the trends in the emission line ratios as a function of the density of the electron density of the ISM. And you can see that most of these emission line ratios kind of increase towards lower and lower ISM densities, or electron densities in the ISM. And one of the main reasons for this increase is because your temperature of the ISM also keeps increasing, which is this top panel here. So the temperature of the ISM also, because the temperature of the ISM increases, you have more and more ionization, collisional ionization as well, from and which gives you more ionization of N2, S2 compared to H alpha. And so that's why your emission line ratios increase with lower electron densities. That is one factor. The other factor, which is shown on the right, is that as you get to these lower and lower densities, ISM densities, the radiation field also becomes harder and harder. The spectra of the radiation field becomes harder. So if you have these very high densities, so gas in these very high densities surrounding these newly formed stars, then they absorb most of the radiation from these newly formed stars. But the spectra of these newly formed stars is not hard. So most of the radiation goes into these hydrogen ionizing bands. But as you go to higher and higher, older and older age stars, as you can see here from blue to red, the spectra becomes much more and more harder because of this Wolf-Rayet phase. And so the radiation field itself gets much, much harder. And so as you get to larger, higher, older and older stars, the probability of ionizing higher and higher elements becomes bigger. So here on the bottom panel here, I show the ionizing radiation the amount of ionizing radiation for oxygen plus compared to the normal value. And as you see that the ionizing radiation intensity increases with as you increase the density of the ISM. And that's mainly because of these old stars, which are no longer cocooned by this high density gas, because the supernova feedback has basically cleared out these H2 regions. They are now able to shine their harder radiation field into this low density ISM. And because this harder radiation field is getting to these lower density ISM, they can start to ionize these more ionized metals. Like instead of O1, you have O2 and O3 being present in this low density gas. Okay, so that was simulations from these were not, most of the results I showed before were not cosmological simulations. These were isolated galaxy simulations of a Milky Way-like galaxy mostly. So now we have basically tried to do this in a cosmological setting. So basically we take a large simulation volume, and then we resolve a single galaxy with a lot of resolution elements. And we have called it the Thiessen-Zoom project. And our primary aim is to understand the physical processes that dictate the ISM conditions in these early galaxies. We are mainly looking at galaxies beyond redshift 3 in this project, but of course we can also do low redshift science as well. So the first thing to note is that we kind of get the right stellar to halo mass ratio. That is a given. I mean, we kind of almost every simulation has to get this right. Otherwise, we won't get the other properties right. And many simulation groups have shown this already. So as a function of redshift from all the way from redshift 9 to redshift 3, we show the stellar mass as a function of halo mass of the galaxy. The blue-black line is the Behroozi relation from the universe machine. And all the colored points are the different galaxies in a simulation. We kind of match it. We also get the right metal and dust abundances. So on the left is the mass metallicity relation for the gas in these galaxies. And you can see we kind of match the observations here. Some of these are new observations from JWST, although we seem to have a steeper relation than what some JWST observation seems to predict. We can also look at the dust to gas ratios because, as you know, we model dust as well. And so we kind of get this relation where the dust is kind of constant. The dust to gas ratio is about 0.01% in these very small galaxies. And then it increases to about less than 1% or so in these very high metallicity galaxies. And the black line here is a semi-analytic model of dust formation from the popping. There are very few observational points here, so I have to rely on semi-analytic models to figure out if we are doing the right thing or not. And we seem to be in the right ballpark. And in these cosmological simulations, we can also look at the Kenniket-Schmidt relation. So here is the star formation rate on the y-axis, the total gas on the x-axis. And most of our galaxies seems to follow, even at high redshift, they seem to follow the local main sequence. But there are some galaxies which also seem to be in a starburst phase, and they seem to follow the Kenniket-Schmidt relation given by the starburst phase. So the gas depletion times are smaller. Of course, I'll just say that these are all preliminary results. As you can see, it's an in-prep paper. So stay tuned for many more results that will come out of this project soon. Okay. Of course, despite all these good predictions that we can make, there are still some problems with the kind of models that we use. So one of the problems here I show is the problem of very high luminous galaxies seen at high redshift by JWST, right? And we don't know how you can form such highly luminous galaxies at such high redshifts. Okay, so there have been a couple of papers which discuss this, and there have been many papers which discuss this, and I just showed two here. So the one is from Avishai Deckel, who show that the stellar winds from very low metallicity stars are not as efficient. You don't have a lot of power in the stellar winds for low metallicity stars because they're mainly line-driven winds. And so, of course, if the stars are of low metallicity, you won't have such high winds, right? So they claim that because you have this almost feedback-free 4 to 5 million years in the beginning without any stellar winds, you can actually form a lot of stars in this very, very initial phases of galaxy formation in the very early stages of the universe. Okay. Another paper I would like to talk about that I show here is by Shyam Menon, they recently came out with a paper showing that you can have, if you have these very low metallicity environments, then the dust will also be low because the amount of dust in these environments is also low. And so the radiation pressure on dust will not be high. So the radiation pressure cannot really disrupt these giant molecular clouds. And because you do not have this efficient feedback, you can actually form stars with a very high efficiency in these low metallicity, low dust, high density environments. So both these processes seem plausible. Either of them might be correct, both of them might be correct, but we don't know which one is the right solution to this problem. And one of the reasons we don't know the right solution is because even with these high resolution simulations, you're not really resolving all the processes that goes on in the ISM of these galaxies. Okay. because even with these high resolution simulations, the impact of these processes happens on parsec scales or so, and they are still subgrid in most of these simulations. So you can partially resolve them, but you cannot really fully resolve them. And if you cannot really fully resolve them, you cannot say too much about which physical processes are important in what kind of environments, okay? So one way to get around this is to resolve all the relevant processes. Just go all in and try to resolve these galaxies with as many resolution elements as you can. And so one such example, there is the recent Regal simulations, which came out a month or two ago, where they do these isolated dwarf galaxy simulations, where we do these dwarf galaxy simulations at a resolution of 1 solar mass or so, and a spatial resolution of 0.0004 parsecs. So that's really, really high resolution. And with this kind of a resolution, you can actually resolve all the fundamental physical processes that goes on around stars, like photoheating, photoionization, radiation pressure, cooling, supernova feedback, etc., etc. And so I refer you to this this paper here for more details, but it has full radiative transfer, accurate low temperature cooling, and it has IMF sampling of individual stars, and it has winds and supernova as well from first principles. And so here in this paper, we show how the impact of full radiative transfer can actually impact the star formation rate of galaxies. So these are two different simulations with two different metallicities. So the green is higher metallicity, 0.2 solar. The red is lower metallicity, 0.02 solar. And the blue is 0.02 solar, but without any radiation fields involved. And you can see that if you include the radiation field, you can decrease the star formation rate by almost 2 orders of magnitude in these low mass dwarf galaxy simulations. And the reason is you have this, the reason is you have this early stellar feedback from radiation fields, photoheating, radiation pressure, etc., which clears out the environment of these new around these new stars. And so your supernova basically goes off in these lower density environments, which makes it much more efficient to drive outflows from these galaxies. Okay. And so this is not something new. This has also previously been seen in other works from Rosdahl and from my work as well. But these are these first time we are actually seeing in this full galaxy scale simulations with this very high resolution. And so what this can do is to try to inform us about how star formation happens. So here we just show one such example. So on the x-axis is the total pressure in the disk of the galaxy. Under the y-axis is the total star formation rate surface density. Okay, and so the green and the red are full RT simulations, and the blue is no RT simulation. And the black line here is what is predicted from this pressure regulated feedback modulated model from Kim and Oestreicher. Okay, and you can see that the no RT simulations kind of match the model from Oestreicher and Kim, but the full RT simulations predict that the star formation rate should be lower for a given pressure in the ISM. Of course, the caveat here is that the PRFM model, the line here is taken from full solar metallicity simulations, whereas we are looking at subsolar, much subsolar simulations. So, but there was a recent paper by Chang-gu Kim looking at how metallicity affects this, and we haven't really checked with that paper yet, but it'll be interesting to see if their scaling with the metallicity agrees with what we see in our simulations as well. Okay, so finally, in the last 2 minutes or so, I'll say that, of course, doing these solar mass simulations are really, really important, and they can tell you a lot of things from first principles, but they're really expensive. And that's the reason we can only do dwarf galaxy simulations now. We cannot really do even Milky Way size simulations because they are just too expensive. But fortunately, the computing is also getting much better. So I just show here an example of the Frontier supercomputer that just came online a year or so ago, which is the first exascale machine in the world. And the way they achieve these exascale computing is through these hybrid architectures. So you have like 8 GPUs attached to a single node of that machine. So if you want to take full use of these exascale computing, you need to make use of all the computing resources available on the node. So you need to have the code which is capable of running on this hybrid CPU GPU kind of architectures. Okay, and so that's where we kind of put in here. So we have kind of transferred our repo RT onto GPUs recently, a paper put out by Oliver Zier and me and others. And where we kind of transported all the radiative transfer calculations onto the GPU. So here we are just showing a simple scaling in a cosmological simulation box. And we see that just by transferring just the radiative transfer, the radiation hydrodynamics onto the GPU, keeping rest of the things on the CPU, we can reduce the runtime of the radiative transfer by about 10 to 15, and the total runtime about a factor of 3 to 4. And there are plans to actually put all the other parts onto the GPU as well. And so by going to these very sophisticated numerical techniques, we can actually hopefully achieve and try to run even much higher mass galaxies with this full solar mass resolution in the near future. Okay, so I'll conclude here saying that the ISM is an important part of the galactic ecosystem. You have a variety of processes like star formation, feedback, etc., which regulate the properties of the ISM. I haven't even talked about cosmic rays and magnetic fields. That's a whole other topic, which I haven't touched about. There are a variety of simulation techniques which can give us important insights into the ISM. I showed an example of my ISM model, the Smuggle RT model, which kind of predicts the right properties of the ISM, the molecular chemistry, the dust chemistry, the right emission line properties, etc., and which can help us interpret observations from these new generations of telescopes. Of course, it doesn't resolve all the relevant properties, so there is a push towards going towards even higher resolution simulations, so ideally 1 solar mass resolution. But of course, before we do that, we need to improve our efficiency of our numerical codes, and we hope to do that in the near future. So thank you.
I can't find the button, so I'm just going to click. Thank you for the nice talk, Rahul. This is awesome. So before jumping in for question, let's just go around and see if there's any question from the audience. Going one, going twice. Go ahead, Vinay.
Yeah, it's dust. Of course I have questions, but I thought I'd leave it to everybody else first. Would you be, so the dust distributions, this is one of the first slides.
Right.
So you talk about temperature and gas to dust ratio, but also do you have like a column density map that we can compare, for example?
Yes, sorry, just give me a second.
And would you be willing to share that? And at what high resolution are we talking here?
Resolution of about a few parsecs or so. So this is the dust. Oh, that's the dust to gas ratio. But it's easy to get the column density of dust as well. I don't have the plot here, but we do have that quantity, and it's definitely easy to share that. Yes.
Because it would be I saw Clayton on here earlier, and he has an overlap. We work on an overlapping galaxy pair, so we have actually a backlit dust map of a nearby SC galaxy, so down to a couple of tens of parsecs. So
right.
It would be a direct comparison of like, hey, how do we see the same structures there? So it would be lovely to do that direct comparison.
Yeah, sure, that'll be great. Yes, that's definitely something we can do. Yeah,
I will follow up with you.
Oh, that's great. Yeah.
And so the second one, the dusty outflows. Hey, I was just talking to Aaron about edge-on galaxies. This is big, dusty structures in edge-on galaxies. You showed the Hawk result from 2000. That is for NGC 891, which is the absolutely lovely edge-on galaxy that everyone always shows, but it is also the one with the most possible outflow and dusty
Right.
clouds in high latitude. It's one of 3 known UV halo galaxies, so the ones where UV is scattering off the
Right.
dust at high latitude. So it's I organized an Edge on Galaxy conference a decade ago, and it was like we sort of checked off every time anybody showed that galaxy, because it was like it's
Right.
everybody's SED model galaxy, but might not be completely compatible to the Milky Way. I do like how you had that dusty outflow models, like the comparison with the amount of dust in the CGM, and I was very curious,
Yes.
how did you get that?
What do you
So-
mean by how did I?
So where
I
did the data
just,
points come from?
so where did, sorry,
Where did the data points come from? Because like I recognize
the
some-
observations, you mean?
Okay, but whose observations? Like this is
Whose observations? That's a good point. I didn't put that here.
sorry,
I can, yeah. These are the galaxies from sorry, I don't know which paper. I don't remember which paper exactly, but I can let you know.
because it's the way that usually is done with some sort of background source, like
Right.
or something. And so it's very curious how that was estimated, because actually looking at higher latitude dust was something that we tried to do with Herschel, and it was very, very hard. So
Right.
actually seeing numbers here is exciting.
Well, you can see the error bars on the observations, right? I mean, there are a few which are quite constraining, but yeah, I mean,
the fact that they're there at all is
yes, sure. I can send you. I don't remember which paper I took this from, so but I can send you the yeah.
And yeah, we have and so we also have emission lines for that same sort of overlapping galaxy. So we observed it with IFU. So we have a metallicity gradient. We have emission lines. So it would be a really neat thing to compare.
Yeah.
The emission line map that you have, an extinction map, if you can make it, or just a column density map that we then translate into an extinction, like full throughout the disk extinction map. And that would be great. Comparison.
We have all of those for Milky Way and an LMC. So these are isolated galaxies. We don't have a large sample. We have 2 galaxies, but we can give it them to you if
yeah, this is an SC galaxy that's very compatible to the Milky Way, I would say.
Right. Sure. Yeah.
Size-wise. Okay, and kept writing down little.
I see that Clayton chimed in the chat that says we also have emission line IFU data to compare to as well.
Yeah.
So Clayton, feel free to unmute and chime in if you want to say a bit more about it.
Yeah, we have attenuation fits in multiple different wave lengths using overlapping galaxies, as Dr. Horford has already mentioned. We also have Jason Young is also in this meeting as well. He's the one that he and Dr. Horford did the observing in ground-based telescope in McDonald Observatory that got IFU emission line data of the spiral SC galaxy that is very similar to the Milky Way. And so we are able to with what you've been showing us, this is a great opportunity, I think, to follow up.
Yeah, that'll be great. Yeah.
The next 2 good reasons to come back in the fall, actually.
Yes.
So Clayton and Jason both will be speaking in the Galaxy SIG seminar in the fall. So stay tuned for a full schedule. But yeah. Great. Any other questions from the audience? I got one quick one, Rahul. So I'm curious too that you showed the stellar mass function from these on Zoom. Is that right? It matches observation quite well at redshift 9, but they overshoot at redshift 3.
Yes.
Oh, these are stellar to halo mass ratio. So I'm curious, is there any quenching mechanism included in the simulation? Is there AGN feedback?
No, there is no AGN feedback.
It's not this mass range anyway.
Yeah, they won't affect this mass range. Although I don't know. I mean, the Beruzzi seems to be quite a bit lower. This is 2019, lower than even the 2013 results, and there is some, I don't know, some leeway about how high or how low this can go. So it seems to match very well redshift 9, as you say, but yeah. We haven't really looked really carefully into why we don't match this at lower redshifts, but yeah, that's the best we could do with this model. Yeah.
Almost lead me to, as just thinking out loud as I speak, maybe there is some observation bias towards galaxy at these stellar mass, maybe only the bright stuff get detected.
Yeah,
First stellar mass is
sure. Shouldn't that be more? So generally, this I didn't show a slide here, but the star formation rate is burstier at higher redshift. So that you should be seeing more higher. Maybe that's why that's one of the explanations for this high luminosity functions in JWST, right? So maybe I don't know. I don't know if that's still a problem at redshift 3. Do you expect to see a lot of as bursty galaxy at redshift 9 as 3? I'm not sure, but
no. That's why I first asked if there's quenching mechanisms or feedback that.
The feedback, sure, but not AGN quenching.
No. Yeah, other feedbacks like.
So yeah, then we like stellar feedback is present, but not AGN. So that's one of the slides I kind of didn't show was I think here we are trying to like quantify the burstiness of the galaxy by plotting the power spectrum here, and it seems that the galaxies at redshift 10 are much more burstier than galaxies at redshift 4. And this is partial explanation for what JWST is seeing, but I didn't put this slide in because I don't understand this plot well either yet. So hopefully we can, we'll have some more results soon. Yeah.
Thanks. Yeah, I'm also thinking with all these recent little red dots observed by JWST, start to worries me that maybe black hole do play a role, maybe not as big as AGN feedback redshift 2, but some role that influence the evolution of galaxy in the past.
Yes, so that's one drawback. We don't have AGN feedback or AGN modeling in this simulation, so we cannot really say anything about the AGN, unfortunately, with these simulations. But yeah, that's one of the improvements that we have to make at some point in the future. Yeah,
I look forward to that.
Yeah, sure. Yeah.
Okay. Any other questions from the room? Going one, going twice. Not everyone can get 10 minutes of their life back. This recording will be made available on YouTube afterwards, so feel free to go back and watch it. Okay, all right. Thank you, everyone. This is the last scheduled talk before the summer, and we'll come back in the fall. Look out for an email from Benny and I, and yeah, come back. All right. Thank you, Rahul. Thank you.
Thank you so much. Thanks, everybody.
See you, everyone. Bye.